So in this video, I'm going to start going through topic CC14, which is rates of reaction. This is a paper 2 topic. First thing we're going to do is just look at a chemical reaction. So I've just chosen one at random, and I've got magnesium and hydrochloric acid reacting to give me magnesium chloride and hydrogen gas. In this equation, the chemicals I've got to the left are called the reactants, and the chemicals that I've got to the right are known as the products. You start off with the reactants, in this case magnesium and hydrochloric acid. They react with each other and then they form new products. When we're looking at the rate of a chemical reaction, we're looking at how quickly those reactants are turned into products. In other words, how fast the chemical reaction is. The rate of chemical reactions can vary quite a lot. You can have really quick chemical reactions such as explosions, and then on the other hand you can have really slow chemical reactions like the rusting of a nail. In order to actually calculate the rate, you need two pieces of information. You need to know the change in mass or the change in volume of one of the chemicals involved. So that could be the change in mass of one of your reactants or the change in volume of a product. And you need to know how quickly this change is occurring. So you need to know the time taken for this change. So it's going to be the change divided by the time. If we look at some sample questions on this, you'll see that the calculation is straightforward. In the first example here, it tells me that the mass is decreasing by 58 grams. That tells me that I'm getting a change in mass of 58 grams. So my change is going to be 58 grams. And the time it takes for this change to occur is 233 seconds. So it's always the change divided by the time. When I do that on my calculator, I get an answer of 0.2, just to one decimal place. But as well as my numerical answer, I also need to give the unit. If we look back here at the workings, you can see you've got grams divided by seconds. And that's going to be my units. Grams divided by seconds, or gram per second. Another way of writing the exact same unit is just gram second to the power of -1. Okay, so these two things are exactly the same, either gram dash second or gram second to the -1. They both mean grams per second. It's the same way of representing the unit. In the next example, I'm told that 48 centimeters cubed of gas is produced in 97 seconds. This tells me that I get a change in volume. So the first one I was dealing with a change in mass, now I'm dealing with a change in volume. And that change in volume is 48 centimeters cubed, and it takes 97 seconds for that change to occur. Okay, once again, I've got the change on the top line divided by the time, which is on the bottom line. When I do that on my calculator, I get an answer of 0.5. I'm just keeping these to one decimal place. Again, I need to include a unit. Above, I had grams divided by seconds, but here I've got centimeters cubed divided by seconds. So my unit is going to be cm cubed dash seconds. Centimeters cubed per second. Again, I can write the same unit as cm cubed s to the -1. They mean exactly the same thing. Just one more example to go through. It says the mass of a reactant changes from 43 at the start to 22 at the end. So in this case, you need to work out the change yourself. In the first example, you were given that change, but here you need to work it out. You're told you're starting with 43 grams and you're ending with 22. That means you get an overall change of 21 grams. This change in mass, 21 grams, takes 79 seconds to occur. So once again, it's my change divided by my time. And I get an answer of 0.3. And my unit, again, is going to be G divided by S, or grams per second. Okay, so that's how you would use that formula, the change divided by the time, to work out the rate. As well as being able to calculate rate, you need to know experimentally how you would collect the data needed. So how would you record the change in mass of a chemical reaction as it was occurring? I have drawn picture here to represent the apparatus that you might use. Okay, so I've got a chemical reaction. It's the same one I had above. I'm reacting magnesium and hydrochloric acid, and I'm forming magnesium chloride and hydrogen gas. If I start by putting my conical flask on a mass balance, I can see that at the start of my reaction, the total mass is 200 grams. At the end of my reaction, I can see that I don't have 200 grams anymore. I now have 197 grams. From the start of the reaction to the end of the reaction, there has been a change of 3 grams. By using the mass balance, I can record the change in mass over the course of the reaction. But it's not enough to just know the change in mass, which I can easily see is 3 grams. I also need to know how quickly that change took place, so I need to know the time. Therefore, when I'm doing this experiment, I'm not just going to record the start mass and the end mass, I'm also going to record the time taken for this change to occur. And to do this, I would make myself a little table. And I would start at the very start of the reaction when I've got 0 seconds as my time. And I can see that my starting mass is 200 grams. And then at regular intervals, so I've used 30 seconds, I'm going to keep taking the mass of my reaction. And you can see that it's decreasing, decreasing, decreasing. And I would do that every 30 seconds, okay, until that mass stops changing. So you can see here I've written at 240 seconds that it was 197 grams. It was the same at 300 seconds. It was the same at 360 seconds. So when my mass stops changing, when it stays constant, that's when I know that my reaction is complete. And I can see that my total change in mass is the change at the mass at the start, which was 200, to the mass when it stops changing, which is 197. So my change in mass over this reaction is going to be 3 grams. And the time it took for that change to occur is going to be 240 seconds, because that's when I stopped seeing it change. Then I just do 3 divided by 240, and my unit is going to be grams per second. Just to briefly explain why we're seeing that change in mass, if we go back and look at my chemical equation, you can see that you're producing hydrogen gas. Because hydrogen is a gas and my conical flask is open at the top, as the hydrogen gas is produced, it is going to be able to escape from the conical flask. Because the hydrogen gas can escape, that causes a decrease in mass as the reaction takes place. So the reason it's decreasing is because your hydrogen gas is escaping. If this conical flask was sealed, if it couldn't escape, then you wouldn't see that change in mass. But because you've got an open system, you are going to see that change in mass. Often what you'll see though is they'll use a little piece of cotton wool at the top of the flask. And the reason they'll put this cotton wool in is because they don't want any of the acid to escape. If it starts to react quite violently and you get a bit of bubbling, you don't want any of the acid to bubble out of the conical flask. By putting the cotton wool in place, it stops any acid escaping, but it will still allow the hydrogen gas to escape. And you can use this method to measure how the mass is changing over time, and that will allow you to calculate the rate of the reaction. We also said, as well as recording a change in mass, you could record a change in volume. So rather than just letting all of this gas escape, how about I collect the gas and record the volume. So to do this, I would need the following apparatus. Okay, again, I've got my conical flask, which is where my reaction is going to take place. But instead of having an open conical flask, I have a closed system. I've got a stopper in place that prevents any gas escaping. And then connected to my flask, I have got a gas syringe. And what will happen is as the reaction takes place, all that gas that is being produced will enter my gas syringe and it will be collected there and you'll be able to record the volume. So again, it's not enough to just record how much gas you're producing. You need to know how quickly you're producing. So if I was doing this experiment, again, I would be recording time. So you start off at 0 seconds and you've got no gas in your gas syringe. And then just say for this example, every 20 seconds, I'm measuring how much gas I've got in my gas syringe. And you can see that at the start, it jumps up quite quickly. But then from 60 seconds onwards, the volume stops changing, and that tells me that my reaction is complete. So here, my change would be you're going from 0 at the start up to 26 centimeters cubed. That's the max volume that I had. And the time taken for that change was 60 seconds. So you divide 26 by 60, and your units will be centimeters cubed per second. So you're measuring the increase in volume, and you're doing it over time so that you can calculate the rate at the end. For both of these examples, I was reliant on a gas being produced. Okay? The first method will only work if you're producing a gas. If you're not producing a gas, you're not going to see a decrease in mass. This method is only going to work if you're producing a gas, because you're going to collect that gas in a syringe. But in the following reaction that I've got written here, you can see that you're not producing a gas. You're producing something aqueous, something that's dissolved in water, and you're also producing a solid. So if you're not producing a gas, you can't use either of those methods to measure the rate of the reaction. Instead, you need something different. And what you're going to use instead is called the disappearing cross method. It's a really straightforward technique. You start off with a white tile and you draw a cross on that tile. You then get your chemicals and put them in a conical flask, and you place that conical flask onto the tile with the cross. Because the contents of your flask are clear, you will be able to look down through your flask and see the cross at the start of the reaction. But as the reaction takes place, because you are making a solid, the contents of your flask will turn cloudy. And when they turn cloudy, you will no longer be able to look down through the flask and see the cross. What you will do is use a stopwatch to measure the time taken for this cross to disappear. Now in this case, you're only taking one measurement. You're just measuring the time taken. So with just one measurement, you're not going to be able to calculate the actual rate of the reaction, because you're only just measuring how long it takes for that cross to disappear. But what you can do is you can compare lots of different reactions that all produce a solid. So you could have 3 or 4 different reactions all producing a solid, and you could use this method to see which one is the fastest and which one is the slowest, based on the length of time it takes for that cross to disappear. Another application of this disappearing cross method can be seen in the following exam question. In this case, a student wants to do the same reaction, but it wants to carry out the reaction at different temperatures, and it wants to see what effect temperature will have on the rate of the reaction. Have a look at this question and see how you might answer it. It is for 3 marks. In your answer, you'll have to say what you're going to do. Remember, you're changing temperature. So what equipment will you use to change the temperature, and how will you measure the temperature? You need to tell me as well what would stay the same in every single reaction, so what would act as your control. And then you need to tell me what measurement you would take in order to see which had the fastest reaction. So take a few minutes, press pause, and see if you can answer this question for yourself. Okay, so below I've written out the answer. All right, you need to change the temperature. So I have suggested using a water bath to change the temperature, and then also using a thermometer to ensure that that temperature remains constant and it's not changing throughout the experiment. So you'll get 1 mark for suggesting how you would control or change the temperature. So you can say a Bunsen burner or a hot plate or a water bath, just anything that will allow you to change the temperature. But do mention thermometer in there as well. I need to say what I would keep the same. So in each reaction, you're combining sodium thiosulfate with hydrochloric acid. So I've said you're going to use the same volume, okay, so the same amount each time, the same concentration of hydrochloric acid each time, to keep the experiment fair. Then you also need to say what you're actually measuring. You're finding the time taken for a precipitate to become visible. In other words, if the precipitate, the solid, is forming, you are no longer going to see your cross. So I've written measure the time taken for the cross to disappear. So I've included how I'm going to change my temperature, what I'm going to keep the same each time, and the measurement that I am going to be taking. And that will get me all 3 marks. In the next video, we're going to look at how to use graphs to work out the rate of reactions. There's a lot of graphs that come up on this topic, so the next video is really important for work on graphs.